So, hello engineers, welcome again. So, as we had discussed about the Fourier transform in the last class, uh, I will be Fourier transform. I will be continuing that discussion. So today we'll be going a little slow because in the last class what I realized is I was a little fast. So just imagine like you are given in frequency domain this kind of plot. Okay, just take it. So this is amplitude and this is frequency nu. So this is 1, this is 2, this is 3. So just imagine this has amplitude something 1, at 2 maybe zero point 0.5, and at 3 maybe 0.7. Can you reconstruct? This is the frequency domain uh, informations you are given. Can you reconstruct the time domain signal, actual signal? Yeah, that's very easy, right? Because last class we had discussed the frequency domain, sorry, the time domain signal will just be the linear combination of the frequencies, right? As the amplitude 1 into cos 2 pi into t plus 0.5 into cos 4 pi t plus 0.7 into cos 6 pi t. Okay, simple enough. But look at the expression carefully. Uh, when the the this gap like this is less, like as soon as I decrease the information, like at 1 hertz, as 1.1 hertz, like as the more consistent my frequency, like more continuous kind of thing, more less and less gap, like they are more consistent, the frequency domain signals are more consistent, like the more number of more frequencies are available. Suppose this period, this gap is getting less and less, ultimately this becomes a continuous time signal. It used to be like some summation of nu is equal to minus infinite to infinite a of nu cos of 2 pi nu t. Okay. This used to be our signal. So when the frequencies become continuous, kind of like it's so the repetition is so smooth, like it seems like it's continuous, then my signal, this summation becomes integration. So it will be minus infinite to infinite a of nu cos 2 pi nu t dt. Okay, so this can also be considered as a Fourier transform signal, or inverse Fourier transform signal. But here one problem is that here we have not considered any phase shift, right? We assume all the signals have zero phase shift. Here we haven't assumed the second plot, which is the phase plot. We assumed it has to be 0, 0, and 0 with respect to nu. But in general, whenever we are analyzing some signals, they will be having some phase shifts. In practice, a general signal will have some phase shift. Definitely. Right, not definitely. Like most likely it will be having some phase shift. So how to deal with that? Before moving forward, like I will be just complex number analysis kind of thing. So the phase and amplitude can be described by complex number. How? Like if this is a real axis and this is an imaginary axis, we know in complex number if this is my complex vector or complex number, whatever it is. So the this is the real part. If this is new, this is not new, we'll take another, some maybe k or z. Okay, z. That's a classic nomenclature for complex numbers. So real and this is imaginary. So z is a combination of real part plus j into imaginary part. So this j denotes the imaginary axis, nothing else, the iota, or you can take it as I, whatever feels you correct. And the amplitude, this value, amplitude, this amplitude, what is the amplitude? It's nothing but real square plus imaginary square. And what about this phase? This phase is tan inverse imaginary by real. So similarly, when my there will be some phase shift in my signal as well. Just think of 45 degree unit amplitude is equal to 1. This is y is equal to 45 degree. Then what will be the z? My z will be 1 by root 2 plus I 1 by root 2, right? And it has 1 at an angle 45 degree. This is a polar coordinate and this is the Cartesian coordinate. I'll just note it down. Cartesian. This is polar. Okay. So my f, I can say the signal f nu is equal to 1 by root 2 plus I 1 by root 2. I'll just box it. This has, sorry, just once is equal to 1 at an angle 45 degree. This is a signal with amplitude 1 and with a phase shift of 45 degrees. Okay, you can denote it as so this, like this. The phase shift is of 45 degree. Okay, so what if like I can, and you know the Euler's form, it says in also the sinusoids, and cosines can be described using this Euler form. What does the Euler form say? E to the power I theta, it. E to the power it is equal to cos t plus j or I sin t. Sorry, like the electrical domain nomenclature j that comes to me. Okay, so what happens now? The initial a nu, what we had, a nu cos 2 pi into nu t, now can be written as f of nu into e to the power this cos term, I can represent it as e to the power 2 pi I nu t. Okay, so this has my phase shift also. Correct? So what does this value have? So f of nu is 1 by root 2 plus I 1 by root 2 whole into, if I just cos 2 pi nu t plus I sin 2 pi nu t. So if I multiply it and rearrange the terms, I'll be getting, you can verify the expression. It's 1 by root 2 cos 2 pi nu t plus, sorry, minus 1 by root 2 sin 2 pi nu t plus I into 1 by root 2 cos 2 pi nu t plus I into, minus, beg my pardon, 1 by root 2 sin 2 pi nu t. This will be plus 1. So this part I can say, choose green color as the real part, and this term is the imaginary part. And it's a inherent property of like this kind of the sinusoidal complex analysis is the real parts are in general, are not in general, it's always odd, sorry, even with respect to time, and the imaginary are odd, uh, not, it's not an odd signal, it will be an odd signal, with respect to time. So the negative values get cancelled out, and we ultimately get the expression, like the negative frequencies get cancelled out in the odd sequence. You can do the mathematical calculation. So sum of positive and negative frequency we get as the, simply we only have cos of 2 pi nu t plus the phase shift pi by 4. So now we also get the phase shifted signal. So I think this part, whatever I have explained today, it is like you understood it. Otherwise, if you face any problem, any doubt, you can mail me. My homepage will be in the description, and my mail ID will also be there. Thank you.